when we load a granular material, a soil, under relatively low loading conditions, particles do not exchange neighbors, and there are no significant volumetric changes. However, there are deformations, and all those deformations are taking place at the contacts between particles, like when we place our foot on a soccer ball. All the deformation localizes at contacts. And so, in this small strain regime, contact mechanics will determine stiffness. And so we have to wonder what are the different contact processes that we can identify. And so we're going to organize this in two groups. First of all, when we apply a normal load, and then we're going to reach to the case where we apply a shear load. So in the simplest of all cases, consider a normal load applied to two spherical particles. So clearly there will be a contact flattening here. But let's try to anticipate this behavior. As we are going to add a load, let's measure the deformation between contacts. And imagine that we apply the load in steps. So we are going to apply subsequent amounts of an equal amount of load. At the beginning, the contact is infinitely small. So any load implies a very high stress concentration, which produces a pronounced deformation. Now, the next load is actually going to produce a smaller deformation because the contact is does already exist. It has some flatness. And the subsequent load, an even smaller deformation. And you can see how this trend shapes up. The higher the load, the flatter the contact, the lower the additional deformation. This is called Hertzian contact, and was studied by the same individual who actually proved the existence of electromagnetic waves, a great scientist in the 1880s. For smaller particles, there may be attraction forces. Go back and look at the interparticle interaction forces. There may be van der Waals interaction forces, and that additional force makes the particle get a little bit flatter. So we need to change the Hertzian contact by including the van der Waals force, and this leads to a theory called the JKR for the initials of the three authors that proposed it. We don't see this effect in sands or even in silts, but if you are looking into smaller particles, and this became very important, for example, in microelectronic machines, in MEMS, then we need to correct for the van der Waals attraction. More relevant to our normal conditions is that we may have a meniscus at the contact that adds a capillary attraction force. So in this case, we have not only the normal force, but we also have the capillary force. And we're going to talk about this in detail when we talk about unsaturated soils. But you can see that the end force is not just the end force, it's the end force by plus a capillary force that will be modifying the contact. Another situation that may emerge is that particles are not necessarily smooth spheres, and the particles have some roughness. And in this case, we need to recognize that the formations will localize at the asperity contact. So there is both a significant deformation of asperities, plus these asperities are also going to force a pronounced deformation near the contact by stress concentration. So we have the combination of these two, and this leads to another theory which takes into consideration roughness and makes the Hertzian contact softer. And you're going to see that one as the GW theory, once again, following the names of the two individuals who were involved. Now we can identify other situations. For example, the case where we have a cone acting onto a plane, and that cone will experience very significant deformations at the contact because of high stress concentration, and this is a good example of how asperities interact with each other. And by the way, this is relevant not only for granular materials, this will be also relevant for a fractured rock mass. The last consideration would be what happens when contacts yield, where in the case of plastic deformation, now we can pretty much guess what will be the size of the contact, because the size of the contact times the yield stress will be equal to the applied normal force. Therefore, we can make a rough estimate of the size of contacts that have yielded. Finally, I don't want to leave this board with the deformation subjected by a contact under normal force without reminding you about the DLVO theory, which is the interaction between particles through electrical attraction and repulsion. So this is the combination of double layer repulsion and van der Waals attraction. And if you remember from particle-particle interaction and water in small particles, earlier videos, you will remember that if I plot the repulsion and the attraction components of the force or the potential versus interparticle distance h, if there is low electrolyte concentration and double layer repulsion prevents, there is repulsion until they are close enough that attraction takes over. However, if there is high ionic concentration, attraction will prevail from the beginning. And if you see, these are inherently, so this is when ionic strength, which is the concentration valence square, increases. As you can see, these are highly nonlinear. In conclusion, whether we start with the Hertz and modifications of Hertz, or we end up with a plastic contact or a total electrical interaction contacts, these are inherently nonlinear. So folks, we can categorically conclude that soils, because they are granular materials and because the interaction between grains happens through contacts and contacts are nonlinear, therefore we conclude that soils are inherently nonlinear. The equations on the board summarize the Hertzian contact. It's a selected set of equations for a purpose. First of all, this is the equation for that line, a power equation, that tells us that the deformation between the centers of the particles is proportional to the size of the particle, but most importantly, scales with the load applied to the 2/3. So it has a 2/3 power. Notice that I could push this transition from the particle scale to the macro scale by relating the strain as delta over 2 radius, and by relating the normal force to the stress by distributing that normal force to the equivalent area of a particle, not just the cross-sectional area, but the equivalent area, let's say in a simple cubic packing, by 2 radius squared. Diameter times diameter is that square area that is actually loaded there. So I could replace this n by sigma times 2 radii squared, 4r squared. And so now I begin to have a relationship between strains and stress for a Hertzian type behavior. The other equation that is quite relevant is how does the size of the contact increase with the applied load. And the size of the contact here would be this little radius, is the radius of the contact. The radius of the contact also increases with a normal load by the cubic root. And in fact, because I have 4r squared here, I can replace that n by an equivalent macroscale stress. But now, please recognize that the shortening divided the distance between the centers. This is a measure of macroscale strain. Is related to the size of the contact. So now I get once again a relationship between strain and stress for a Hertzian type behavior in a material where all the deformations are taking place at contacts without fabric change because we are in the small strain regime. Now, once I have done that replacement, then what I'm really saying is I'm talking about stress versus strain, and I wonder what is the tangential strain at any point, and the tangential strain normalized by the stiffness of the material that makes the grain, the mineral stiffness, then it is related to the size of the contact, which is related to the applied stress. So summary, if I do all these substitutions, I get that this is the tangential stiffness is proportional to the applied stress cubic root. To make this dimensionless, here we divide by the modulus of the mineral. And so the stiffness scales with the cubic root of the applied stress in a granular material made of smooth spherical particles. Other conclusions to recover from here is that the stiffness depends on the contact area at that particular moment, the tangential stiffness. So it could have happened that the contact became flatter because I applied the normal load, but the contact could have become fatter and flatter because of creep. And so imagine that this is granular salt or lead shot or any real material with diagenesis. And so creep will increase the contact size. But there is one more possibility, and that is that the particles get coated with a cementing agent, and now the contact is much larger. And so cementation has a huge effect on the small strain stiffness, so this is cement. And what is important is that Hertzian theory, contact theory, tells us that the tangential stiffness is just proportional to the size of the contact, and it doesn't care instantaneously at that point what created that size, whether it was the normal load, it could have been creep, or it could have been cementation. This is very powerful because now we can understand the small strain stiffness of granular materials, which will be the topic of the following video. The previous images focus on contact behavior between spheres, a cone and a plate, and the DLVO interaction under normal load. And we concluded that soils are inherently nonlinear. Now let's see what happens when I apply a shear load. In this case, we are going to apply, at the particle scale, we are going to apply a shear force. Clearly, I cannot apply just a shear force because there is no shear resistance in a contact that is of frictional nature. So I need to apply first the normal load and then the shear force. So this goes first and this goes second. Otherwise, the system will not be stable. So this is already giving us a hint that the load history is going to be critical in this case. Now let's see what happens at the contact. I'm going to zoom in at the contact, so in this region, and you're just going to see the upper particle, the contact, and the lower particle and the contact. So when I apply the load N, the stress distribution at the contact becomes a parabola. This is what Hertzian theory predicts, in such a way that if I integrate this normal stress across the area of the contact, I recover the applied force by equilibrium. Then, while this is applied, I'm going to impose the shear. Once again, we're zooming into the contact, and when I apply the shear force, now if there is no slippage at the boundaries, this is the distribution of the shear stress at the contact, in such a way that the integral of the shear stress across the contact will be equal to the applied shear force T. Now here is a problem, because you see we have a very high shear applied at the edges. However, there is very small, in fact zero, normal stress. And if we assume that the Hertzian is the contact is frictional and that it follows a Coulomb's law, then the tau ultimate at any point has to be mu sigma. And so if I take the sigma and I multiply sigma times mu, I get a distribution here that looks like this. This is the tau ultimate that the material can deliver. However, this one was the tau required. As you can see, we exceed the capacity of the frictional contact. We exceed it, and so the contact cannot deliver that amount of shear. Now, it has to remain in equilibrium, so what it does is it will follow the admissible, and then it will increase more shear in the central parts. So the actual distribution of shear is the following. And if you have been able to follow this, let me put a little bit a clear drawing to show you where the amount of shear that is applied. So this is the actual condition at equilibrium. Now, as you realize, up to this point, the required shear has exceeded the ultimate shear, so there is slippage here, and there is slippage here on the other side. In other words, there is an annulus of a slippage. And so slippage has taken place. And now we have very important implications. In a granular material, contacts are subjected to normal and shear forces because of the multiple orientations. This is not just a simple cubic packing vertically loaded. That means that there will be slippage at contacts, and because there is a slippage, whenever you push a body over a surface and you stop pushing, it doesn't come back. That means that all contacts are inherently non-elastic. This is a very important conclusion, folks. From Hertz and Hertzian type behavior, all contacts under normal load, because of the stress concentrations and the nonlinearity of that behavior, the macroscale response of a soil is inherently nonlinear. Now, because there are shear at all contacts, then we can also conclude that the behavior of the soil is inherently non-elastic. This has very important implications because it means that the behavior of soils will be hysteretic. When we load and unload, we don't go back through the same unloading curve, and we have these hysteresis curves, which means high energy consumption in loading and unloading. It also confirms that because the behavior is non-elastic, the superposition principle doesn't apply. In other words, it's not the same to apply the normal force and then the shear force, or in reverse order. As we noticed intuitively before, the loading is, the response is load history dependent. Very important implications. And now there is no regime where we can actually talk about linear elasticity, even though we make extensive use of linear elasticity in our analysis, which speaks very highly of the robustness of linear elasticity and the fact that we can linearize any process locally, like a Taylor expansion. I have to make a caveat that in order to trigger slippage, there has to be a displacement at contacts, let's say, of 1 angstrom to break bonds in this region. And so there may be a threshold level. If we impose a minimum of 1 angstrom deformation, there will be a threshold level for true elastic behavior, even in granular materials. But I think that the real take-home message is that from a point of view of contact mechanics, we can categorically conclude that soils are inherently nonlinear, non-elastic, because soils are granular materials.